So I don't know what your goals and motives here, but
Okay, here we go. Some recap questions. How do we measure total carbohydrates? Go ahead.
You take all the amount of everything else, and then you can sort of find that value. And then you
Yes, we can do that. What we can get the total carbohydrate by getting ash, fat, moisture, protein, and subtract that from 100. But if we have a simple matrix, like a juice, or let's say next week you'll be doing 7-Up and beer. What was the method, do you remember, that you're gonna do next week in lab? Go for it.
The phenol sulfuric method.
Yes, phenol sulfuric acid method. So it's based on digesting or hydrolyzing the glycosidic linkages with the concentrated acid, which is H2SO4. And then also the concentrated acid, this reaction is going to generate heat. And with that heat and high acid concentration, you're going to convert monosaccharides into furans. And furans are going to react with phenol reagent to get a colored compound that you'll be measuring with a spectrophotometer. So you'll use glucose as a standard, and you're going to construct the standard curve and determine the concentration of the sugars in your sample. The one thing about this method, it is not meant for complex matrices due to interferences. It is non-stoichiometric. That means it's highly dependent on the structure of the substrate rather than just the concentration of the substrate. That's why the standards, one of the disadvantages is that if you use glucose, it might not give you the true value of your sugars if you have other monosaccharides in. So we talked about preparatory steps. So what are the most common preparatory steps you would do? Go ahead, Taylor.
Drying using vacuum oven and fat extraction using cyclone.
Yes, so we do defatting and we do drying. We start with drying and then we do defatting. Drying can be done with vacuum oven, but if you say freeze drying, that's okay too. Defatting we can do with Soxhlet, or we can do batch extraction with hexane. And then you will have less interfering substances for carbohydrate analysis. So how do we extract mono, di, and oligosaccharides? What are they soluble in that the proteins and starches are not soluble in? Do you remember? Go ahead, Sarah.
hot 80% ethanol.
Yes. 80% ethanol with heat will allow these mono, di, and oligosaccharides to solubilize, whereas large molecular weight polysaccharides and proteins will precipitate. I would say name one method that could be used to determine mono, di, and oligosaccharides.
HPLC.
Yes, we're going to talk about HPLC in this lecture, but we talked about a method or several methods based on what characteristics of the sugar. Mono and disaccharides usually are what? Reducing. So we look at the one of three methods. The Smogy-Nelson is the most common one. Is based on the reducing power of the sugars, reducing cupric containing reagent into cuprous. And there are several methods to quantify, either by gravimetric measurements, titration, or spectrophotometer. Okay, so that's where we stopped. And then there are enzymatic methods to determine mono, di, and oligosaccharides. And usually these are assay kits that we can buy and they're easy to follow. You get the enzyme, you get the substrate that you need in the kit, with the exception, obviously, of your reducing sugars in your sample, or mono, di, and oligosaccharides in your sample. So enzymes are catalysts, biological catalysts. They're very specific, and they are used to measure substrates. And these substrates are your sugars, either mono, di, or oligosaccharides. And oftentimes, because they're based on spectrophotometric measurements, oftentimes we need two reactions. So the auxiliary reaction, or also known as measuring reaction. So let's say you're looking for glucose, you react it with a compound, and then you get a product that still does not absorb light. So it's not sufficient to get the concentration here. So we have another reaction, we call it indicator reaction, another enzyme. That's why often we call this coupled reactions. We're going to talk about enzymes in a different lecture, but in many cases, we need a coupled reaction where we have a first reaction, and then the product from the first reaction, we have another substrate, and then we get another product. So in this indicator reaction, you either have this new substrate that we add here, or one of these products will absorb light. So this is the indicator reaction. So that's the reaction that is either here color that gets reduced, or reaction that cause chromophore production that we can use spectrophotometer to analyze. So that's why with enzymatic reaction, we often have these coupled reactions. So here's an example for measuring glucose. We react glucose with ATP. We add an enzyme called hexokinase. That enzyme is going to allow the covalent linkage of one of the triphosphates here to react to covalently link to glucose, giving you glucose 6-phosphate. That means phosphate is attached to carbon number 6. So we take this substrate, then we add another enzyme, glucose 6-phosphate dehydrogenase, and we react it with NADP. So what happens is hydrogen will be lost from the glucose 6-phosphate to give you NADPH. This is the compound that will absorb UV light. So that's where we do the measurement of absorption of this compound, and we relate it to the concentration of glucose using standards. So with enzymatic reactions, we have a lot of enzymatic kits to determine specific concentration of fructose or glucose or galactose, these are from monosaccharides, or we can do oligosaccharides or disaccharides, lactose, maltose, and sucrose. And we can also use enzymes to determine the concentration of total starch and amylose and amylopectin specifically as well. So we'll learn about that when we collect the starch analysis. So advantages of the enzymatic methods. So you can buy them, the assays are available, so they're easy, you follow manufacturer instructions. So, and then they're usually very specific to the substrate and have low detection limits, so very sensitive. Disadvantages, because it's based on spectrophotometric methods, so you might have interfering substances that absorb around the same wavelength for that particular assay, and they are not always 100% specific. That is because the purity of the enzymes. So sometimes we buy an enzyme that is probably 97 or 98% pure. There might be other enzymes in there as impurities that cause detection of other components. Chromatographic methods for determining of mono and di and oligosaccharides. those, we have the qualitative methods that we talked about earlier, the paper chromatography and thin layer chromatography. So there are screening methods just to determine the different, let's say, composition of those sugars in your sample. If we use paper or thin layer chromatography, oftentimes we visualize by autoradiography. This is just FYI. I won't necessarily ask you to tell me what type of paper or what type of PLC used, but just general knowledge that these are used. Not very common, but they're there. Now I'll spend some time talking about liquid chromatography and later on gas chromatography used for monodiene oligosaccharides analysis. So we explained when we were talking about chromatography earlier in the semester, we explained that sometimes the same compound can be analyzed by different modes of separation. We usually pick one of these based on what we have in the lab, what columns we have, what we have expertise, what publications are out there. But all of these have been used for analysis of mono and diene oligosaccharides. So we can use normal phase, reverse phase, anion exchange, and cation exchange. And I'll give you examples of all of that. So earlier in the semester, we learned principles, and from now on, we're going to get applications on use of chromatography. So what do you remember about normal phase? See how much you remember from your chromatography. Ingrid?
The mobile phase is non-polar and the station is.
Very good. So good thing you remember. Very good. So in normal phase, the separation is based on polarity in this case, with the most polar reacting the most with your column because it is a polar stationary phase and will elute last. And the least polar will interact the least with your stationary phase and will elute first because your mobile phase is non-polar. In reverse phase, it's the opposite. What about anion exchange? What's your stationary phase made up of? You guys studied this. Okay.
In the anion exchange, you're trying to collect anions, so your stationary phase is actually anions.
Yes, absolutely right. So your stationary phase has positively charged functional groups, can be weak base or strong base, and we're exchanging anions in your sample, and we are separating based on the affinity of the anions to the cation exchange, to the cation column. Sorry, the cation exchange is the opposite. Okay, now that with remembering these, let's look closely at normal phase HPLC for separation of monodiene oligosaccharides. So stationary phase can be unmodified silica. So basically, silica groups can interact, the silanol groups of silica can interact very strongly with the hydroxyl groups of carbohydrates based on polar interactions. So we can get good separation actually, sorry, because you have very strong interaction. So if you have a lot of monosaccharides in your system, all these monosaccharides are going to interact the same way with the column and it will be hard to separate. So replacing unmodified silica when we have a mixture of monosaccharides or a mixture of mono and disaccharides that would be hard to separate just without anything else, we use chemically modified silica. So the silica stationary phase is bonded stationary phase, and we call it hilly. Like we had hydrophobic interaction chromatography, here we have hydrophilic interaction chromatography. So it's very similar to normal phase, where the stationary phase is actually polar and the mobile phase is non-polar. But in this specific case, you have silica bonded to a reactive group such as amine. So amine bonded stationary phase. So there is your silica and you have an amine group here attached to the silica, that amine group is going to form hydrogen bonds with the OH groups of the sugars. So that's the type of interaction, hydrogen bonding interaction of the amine group and the OH groups of your sugar. So, like I said, it's similar to normal phase. So your mobile phase starts off as mostly non-polar with high percentage of acetonitride. And obviously, like any chromatography, we can change the rate of the elution, with increasing the temperature of the column and enhancing resolution. So mostly when you have amine bonded stationary phase and interaction with hydrogen bonding, so monosaccharides elute first. Those that have the least available OH groups. So fructose has less available OH groups than glucose, although they're both monomers. So fructose will interact the least with the column. It has less OH groups, followed by, let's say, glucose, and then the disaccharides will come. Well, that's another monomer. But then disaccharide like lactose, for example, or sucrose will come back later. So the more OH groups you have, the more hydrogen bonding you can get with the column, the more retention, and then we will do less. So order of retention is mono, di, oligosaccharides, with the mono that have less OH groups coming out first. So the detection usually is with refractive index detection. Do you remember why we cannot use gradient elution with refractive index?
It's when the light will pass through different mobile phases, then it will change the refractive index.
Yes, so if we're changing the gradient, we're also changing the refractive index, then that will interfere when your actual sugars are coming out of the column. It will be hard for detection. Also, refractive index is not very sensitive. It doesn't have a, you need high concentrations, and also not specific. It's mostly a universal detector. So drawbacks of amine bonded, because you're having an amine group, under certain conditions and with extensive use of the column, you might get shift-based formation due to Maillard reaction. So, and then you have blockage of functional groups of the column. So that will reduce the efficiency of the column, the capacity of the column. So it would degrade over time quicker than any other regular columns. So that's a drawback, but we can fix that sometimes with modifiers. That means regenerating of the column by adding in the mobile phase modifiers such as compounds with diamines. So two amine groups, an amine group that can regenerate the column and interact with silica, and an amine group that would be available to have hydrogen bonding with the sugars. There are other types of columns that are not necessarily amine bonded columns. There are different functional groups that can be attached to your column, and also can form a polar interaction with your sugars. But the most common is the amine bonded. So if I ever ask you for an example, do remember the amine bonded scenario. Reverse phase is also used, but it's very difficult to get separation. So in reverse phase, especially for monosaccharides, so in reverse phase, the most polar will come out. So if you have fructose and glucose, why won't they be separated? They will come out very quickly together because they're very polar. They don't want to interact with your stationary phase. They will come out together and they can hardly be separated. Another issue is that sometimes you have anomers. So anomers, by definition, are very closely related stereoisomers. So if we look at these two anomers here, we have the exact same structure with the exception of the carbon one. That's why it's called anomer. Carbon one has these groups reversed. So OH up here, OH down here. So when you have these anomers in solution, these stereoisomers, sometimes you have a split peak. So you don't have one peak, you would have split peak. To avoid split peaks, what you can do is actually add amine groups in the mobile phase. It causes anomerization, so everything will be in one form. And therefore you would get one single peak in one separate. Anion exchange. So because we're separating small molecules, we use a highly cross-linked resin, and it's the polystyrene dimethyl. So it's highly cross-linked. It's very suitable for small molecules. And how can we make sugars negatively charged? So sugars obviously don't have a charge at neutral pH. So that you have all of your OH groups. However, if you increase the pH, so to above pH 10 or 11, the OH will lose its proton and it becomes negatively charged. That's why we say carbohydrates are really weak acids. That means they're not readily going to give you the hydrogen. They're not going to readily be ionized unless the pH is high. Once the pH is high, they get ionized. That means they carry that negative charge. Then we can use anion exchange chromatography, and we use the amperometric or pulse amperometric detection. So it is based on change in conductivity, or once applying a voltage, you get oxidation or reduction of the compound, and then you can measure change in current. So that's kind of a refresher to remember how that detector works from the HPLC lecture. What would be the order of elution in this case? Don't look ahead, just think about it. If you have negatively charged groups, the hydroxyl groups become negatively charged, what would be the order of elution? Would you have monosaccharides first come out, or disaccharides, or bigger? What will elute first? Think about it, Kevin.
I think bigger would come out first because it'd be harder to pull all because they're they would be more.
Think about it, Kevin. You have bigger, you have more or less OH groups.
Oh, got you. So you're still able to pull off all the hydrogen, so there'd be more negativity of the larger ones.
Yeah.
So they would interact.
Yes, exactly. So those monosaccharides will have less OH groups, so you will have less ionizable groups. Then they will interact less with the column and will come out first. So depending on the OH groups, then you have different order of elution based on their interaction with the column. With cation, you cannot make your sugars be positively charged. You can make them negatively charged, but you cannot make them positively charged. So in order to use cation, you use counter ions in your mobile phase. So the counter ions will associate with your OH groups. And that counter ion, once they're associated with your OH groups on the sugars, will interact with the stationary phase. But in this particular case, separation is happening by ion exchange and size exclusion in the same time. So based on the size, the bigger they are, the faster they leave the column, because you have the element of size exclusion as well. And in size exclusion, bigger molecule is moved first. So here we have a combination of size exclusion and ion exchange with the counter ions. So you can use cations, or you can use acid, diluted acid that gives you protons, H+, that can interact with your sugar. So basically, this is a bit less common chromatography for carbohydrate, but it's there, it's used. The other chromatography method, obviously, is GC. We can do gas chromatography, and it's very commonly used to identify different monomers in fibers. So once we get to the fiber section of this chapter, we're going to talk about how gas chromatography used in identifying the composition of fibers based on monomer analysis. So carbohydrates, monomers, and dimers and oligosaccharides, they are not volatile, right? Like your fatty acids, they're not volatile, and they degrade at high temperature. So what do we do? So to be able to analyze them using GC, what do you have to do?
Derivatize them.
Yeah, you want to derivatize them. So like you did with fatty acid, you did methyl derivatization and you produced fatty acid methyl esters. But here for sugars, there are specific derivatizations that you would do. There are multiple types: silylation, acetylation, and triethyl acetylation. So depending on if you're analyzing monosaccharides or disaccharides, you have different types of derivatization. So the different reactions takes place. The first reaction is basically removal or reduction of double bonds into making sugar alcohol. So reduction to sugar alcohol, and then followed by acetylation or silylation. Then you get a volatile compound. So once it's acetylated, in this case, it's volatile, so it can be it can go into the gaseous state and be carried by your gases in your GC and detected. So commonly we use FID, GC FID, like you used in the lab, with a specific column. No need to remember that. You'll use an internal standard, and we can have the internal standard here in this case. And then you can separate and identify different monomers, and this is comes in very handy in determining the compositions of your dietary fiber. Okay. Polysaccharides. So all of that was mono and di and oligosaccharides, but now we're going to talk a little bit about larger polysaccharides, starch and dietary fiber. So for starch, we have different assays we care for in food analysis. First of all, we care for determining total starch. And in certain application, we care for degree of gelatinization of the starch, and we care to know for degree of retrogradation. So these are important in terms of food formulations and shelf life determination. So we want to know under which conditions the different starches that go into our formulation can gelatinize. So we can choose different starches in our formulation. Another thing is starch retrogradation is important from a health perspective and from a texture and liking perspective. Sometimes starch retrogradation is important, like in pasta making. Sometimes starch retrogradation is beneficial from a health perspective if we generate resistant starch, which is non-digestible, you have low glycemic index. Sometimes retrogradation is not desirable, like in bread and stating. So these are important assays. Another one that I don't mention here is the ratio of amylose to amylopectin. It's based on similar assays to determining total starch, but sometimes it's really important because amylose and amylopectin have different functionalities in different food systems. So determination of starch characteristics then is very important. So we have qualitative methods. Sometimes we want to detect presence of starch, nothing else. We don't care about quantity. So we can do that by adding iodine to the sample. So starch has high affinity for iodine and gives you a purple bluish color. In one of the labs, you're going to use starch as an indicator in the presence of iodine-based reactions. So it's used as indicator to give you a blue color and you titrate against that. Also, microscopy is a big deal in looking at the morphology and the structure of the different starch granules. And you can identify unique grains have unique structure for their starch granules. So you can do microscopy to look at qualitative differences in the sources of your starch. Now, what we care here about is quantitative analysis, and it is based on enzymatic analysis. So in order to quantitate starch, we break it down completely into glucose. Now, how do we break it down into glucose? Without looking further, how do you break down your starch using enzymes? What kind of enzymes do you use? Remember, Taylor?
Amylase.
Amylases. So amylases are endo enzymes, so they're going to chop off the large starch molecule into kind of maltodextrins and oligosaccharides. So we want to break them all the way down to glucose. Amylase alone cannot do that. You remember the enzyme that can do that? So amylases make the chain much shorter. Then we use glucoamylases. So glucoamylases they are exo enzymes, so they're going to take one glucose unit at a time from the extremities of the molecule. So exo. Amylases, there are endo enzymes, so they're going to go inside of the molecule and break it. So it's important to remember alpha amylase endo will break down into smaller chain, not enough to get you to glucose. In order to get to glucose, we need glucoamylase. So in any starch kit, you're going to have a combination of amylases, alpha amylase, and glucoamylase that you will use to get to the glucose monomer. Now, I also want you to remember two other enzymes here. Beta amylase is an exo enzyme, but it cleaves 2 to 3 units from the extremities of the starch. Remember that, because that's important for starch retrogradation and starch gelatinization later. So amylases are going to break 2 units, 3 units at a time. Polymerase is another important endoenzyme that is also relevant in analysis. Polymerases is going to break the glycosidic linkage at the chain, at the branch, sorry. So, you know, in amylopectin and amylose, you have chain, you have branches. Amylopectin has more branches than amylose. So polymerase is very specific to alpha-1,6 linkage, which is at a branch, rather than the alpha-1,4 linkage, which is in your linear chain. So another thing I want you to remember is polymerase and beta amylase do not act on raw starch and retrograded starch. It has to be gelatinized starch for these enzymes to act. Okay, so for beta amylase and polymerase to act on the starch, it has to be gelatinized first. And it cannot act on retrograde starch. So keep that in mind. It's very relevant in the next couple of slides. Okay, so we break down the starch into glucose. And then we want to analyze glucose using enzymes. So I gave you the other hexokinase and glucose 6-phosphatase, glucose 6-phosphate dehydrogenase as one coupled reaction, but the more common reaction that comes actually with the kit for analyzing starch is the reaction that actually uses glucose oxidase, where we oxidize the glucose in the presence of oxygen, we get the peroxide, one of the products. Gluconolactone is a product, but we don't care about. What we care about is the peroxide, hydrogen peroxide generated. The hydrogen peroxide generated, we reacted with a specific dye. So the hydrogen peroxide will oxidize the dye in the presence of another enzyme, which is peroxidase. So this is your measuring reaction, this is your indicator reaction, because this is going to be based on the reduction, oxidation of a dye to give you a colored compound, oxidized dye, a colored compound, and that's what get measured. So you want to remember this reaction. So you have, you don't have to remember the structure. You need to remember glucose, adding a glucose oxidase, getting a peroxide, using a peroxidase, reduced dye, oxidized dye. Don't have to remember this. Okay, a reduced dye and oxidized. But you want to remember that this is a coupled reaction. So when we purchase from Magazyme a starch kit, it comes with alpha amylase, comes with glucoamylase, and it comes with these enzymes specific for measuring the glucose after we hydrolyze all the starch into glucose. Okay. Now let's talk about those two important assays that are important in food formulation and determining of changes in structure over storage or when the product is cooled down. So these are important measurements you might come across when you work in industry later. And I asked you at the beginning of the lecture last time, can we use the same method for two different characteristics? Yes, we can, by getting opposite results. So again, I told you, remember pollinase and beta amylase. They don't act on raw starch. They don't act on retrograde starch. So basically, if I want to determine degree of gelatinization, I add pollinase and beta amylase. The higher the degree of gelatinization, the more the activity is of these two enzymes. They're not going to act on raw starch. So higher degree of gelatinization is going to give me a high activity of these two enzymes. So pollinase is going to debranch. Beta amylase is going to break down into maltoses and maltotrioses. These are reducing sugars. So first debranching, then beta amylase is going to produce maltose and maltotriose. Reducing sugars, then I can get any of the reducing assays we talked about, say Smuji-Nelson, to determine the amount of reducing sugar formed. The higher amount of reducing sugar formed, the higher degree of gelatin. Okay, now flip side. starch is gelatinized, we want to determine retrogradation over storage or during cooling in the process. So we want to determine how much of that gelatinized starch got retrograded. Same thing. We use these two enzymes. The higher the degree of retrogradation, the lower the activity of these enzymes. They will produce less of these reducing sugar, then you will have less reducing sugar in your acid. So opposite results, same method. Okay. Questions? All right. I didn't know I'll go that far today, but here we are. You're quiet.
Yeah.
Yes,
Just slow you down a little bit then.
yes.
The degree of gelatinization and degree, does that change over the shelf life, or is that like inherent to the starch?
It changes because gelatinization occurs only during processing.
Yeah, okay,
So after processing, sometimes you want retrogradation to happen very fast, like in pasta.
Right.
And sometimes you don't want it to retrograde because it will change the structure, physical texture. So that is after processing, you will get it. Now, the degree of gelatinization and retrogradation is dependent on the type of starch you have.
yes.
Yeah,
Okay.
so the type of starch dictates how much gelatinization you're going to see in a certain period of time under certain heating conditions and retrogradation. So especially the ratio of amylose to amylopectin.
Okay.
Yeah, that's going to impact. Very good question related to chemistry. I love that. So yes, different ratio of amylose to amylopectin is going to definitely impact the rate of gelatinization and the rate of retrogradation. Okay. Any slowing down questions? I'm ready to go into fiber. Okay. Last chance? No. All right. Okay, so dietary fiber basically is the component that in our food that we consume from plant sources, but we cannot digest. So basically, that's why we say resistant starch can fall under retrograde, under dietary fiber. So retrograde starch is resistant starch. So anything we consume that cannot be hydrolyzed is going to, from plant sources, is going to be considered as dietary fiber. So dietary fiber includes polysaccharides, includes some oligosaccharides that we cannot digest or break those glycosidic bonds. Lignin, it's not a polysaccharide, it's not a carbohydrate, but it is a dietary fiber. And we often measure total dietary fiber. We measure soluble fiber. We measure insoluble fiber. And sometimes we really need to know the components of our fiber. So soluble fiber, mostly pectin, hydrocolloids. Let's say in oat bran, we have the beta-glucan, which has health benefits. So these are soluble fibers that sometimes we need to characterize and determine how much we have of each based on their health benefits. Insoluble fibers are mostly your cellulose and lignin. You also have hemicellulose. Some types of hemicelluloids fall under hydrocolloids and we are soluble. Other types of hemicelluloses are insoluble. It's kind of like a very complex fraction of the dietary fiber. And then here we have resistant starch. So I said last time I kept mentioning retrograded starch as resistant starch. Do you remember what the other 3 resistant starch types are? Here's your food chemistry check. So we have retrograded starch. What else can be resistant starch? What's the definition of resistant starch? Cannot resist digestion, cannot be digested. So what types of starch are resistant starch other than retrograded starch? I see all the heads down. Nobody wants to look up. Good information to remember. What resists digestion? I just actually gave you a hint of
Fiber.
No, and resistant starch, particularly starch that falls under fiber. Raw starch. Raw starch is a resistant starch. It has to be gelatinized in order for it to be digested, because it will be partially digested if it's raw, not fully. Okay, what else? Modified, chemically modified starch. Chemically modified starch is resistant starch. There is one more.
The whole wheat bran and whole grains, is that talking about like the bran or the angiosperm on the actual plant or not?
So you're kind of like, you're not necessarily, it's not a brand, so starch is not brand, but sometimes the matrix of the food and does not allow the enzyme to physically reach starch. So physically not accessible starch is resistant starch. These are the 4 types of resistant starch that you would normally learn about in food camp. Okay. Now, I'm not going to ask you about that in the final. Just want you to link the classes together. Yeah.
My voice sounds very good. Is like soluble or insoluble fiber like, is one better than the other for you?
Well, each have different physiological benefits. Sometimes for different diseases or prevention of certain diseases, you want soluble fiber, like beta-glucan is linked to anti-cancer in the gut. So, but insoluble fiber is good for digestion, gives you bulkiness, reduce the increase the transit time, and it's good for satiety. So each have different physiological benefits. So dietary fiber in general is good for you. Increase your intake. Okay.
If modified starch is resistant starch and cannot be digested, why do we have it on the back of the product for the ingredient that it has modified starch?
So, well, okay. So modified starch is chemically modified starch. It's not clean label. So we have, they have to put it on the ingredient list. It has to be listed because it's an ingredient. But it follows old regulation, because modified starch has been there for many years, so it was allowed to be used, so it recognized as safe, generally recognized as safe. So it's used, but it doesn't count towards your calories. It's resistant starch, yeah. But it doesn't have any like benefit as a probably just bulking agent. And if you have higher resistant starch than non-resistant starch, you have low glycemic index. Yeah. You slowed me down. Good for you. All right, we'll continue with fiber on Friday.